Right. So the last talk of this session is by Henning Urbat on operational semantics for call by push value.
Right. Thank you. Can you hear me? Good. Okay. So this is joint work with my colleagues Sergey, Goncharov, and Stelios, Tsampas. And this is about abstract operational methods for call by push value languages. So I should better start with explaining what I mean by abstract operational methods. So this is a recently developed kind of high-level approach to reasoning about equivalence of programs in a higher order setting that is based on category theory. And so the kind of equivalence that we discuss here in this context is contextual equivalence of programs, which is kind of the most general operational form of program equivalence. So in this notion, two programs are equivalent if they behave the same in every context. And behaving the same just means if you put them into any context and one of them terminates, then the other one must terminate. So if you think of termination as the observable behavior, this means like there is no observation that can distinguish the two programs. So this is a very well-known and widely used notion of program equivalence, but it has the disadvantage of being a bit difficult to use directly, because ultimately in this definition you have to reason about termination behavior of infinitely many programs at the same time, which of course is prohibitively difficult in general. And so in order to make this usable, we need efficient proof techniques. And these have been developed to a large extent in the last 50, 60 years even. And the two most popular ones are applicative bisimulations and logical relations that we also heard about in the last talk, which appear in many different shapes and forms. And so let me quickly walk you through how this works in principle. And in this talk, I'm mainly going to focus on applicative bisimulations, but everything I tell you today applies in the same way to logical relations also. So let me illustrate this in the case of the simplest kind of language we can imagine, the untyped call by name lambda calculus. So so how does this work? First, we have to specify our language, of course. So we give the syntax and semantics. And of course, for the untyped lambda calculus, you all know it and love it. Well, know it at least. We specify our syntax and semantics. Then we invent our suitable notion of bisimilarity, which in the lambda calculus is quite simple. It just says if two terms are bisimilar and one of them reduces to a lambda abstraction, then the other one also reduces to a lambda abstraction. And if I apply these two functions to the same input, then I get the same output or bisimilar outputs. Yeah? And for logical relations, it's instead you relate related inputs to related outputs. And then the key step is proving that this relation, this bisimilarity, is a congruence, which means that it respects all the constructors of the language. So here in the lambda calculus, it's, for example, the condition that if P is bisimilar to P prime and Q is bisimilar to Q prime, we have to show that P of Q is bisimilar to P prime of Q prime. And if our language has 30 constructors, then we have to prove 30 different compatibility lemmas of this kind. Proving this is quite complex. For example, in the bisimulation case, it requires this thing called house method standardly. And from this, one can usually easily deduce that bisimilarity is sound for contextual equivalence. So if you show that two terms are bisimilar, you can deduce that they are contextually equivalent. Yeah? But the key step here is really the congruence property. Right, so these are very powerful methods. They have been developed for many different kinds of languages in many forms and shapes. They are widely applicable, not only to contextual equivalence, also to other kind of reasoning. But they have the great disadvantage, as already alluded to in the last talk, of being pretty much ad hoc. Yeah? So for every language, for every kind of system, you have to come up with your own tailor-made notions and come up with your own version of soundness proof. So it's quite a lot of work to do for every specific language. And now the question is, can there be maybe an abstract language-independent approach that works universally? And well, of course, the prerequisite for this is that we need to understand all these big words here abstractly. So what is syntax, semantics, applicative bisimilarity? We understand what this means for specific systems, but what does it mean in general? And luckily, category theory gives us the answers in this direction. So there is this framework called higher order mathematical operational semantics that me and my co-authors developed in a series of papers, starting with this POPL'25 paper 2 years ago, which gives us an abstract language-independent approach to contextual equivalence and these reasoning methods based on the theory of algebras, coalgebras, and relation liftings for functors in categories. So it's a very high level of abstraction. And it is a high-level, higher-order extension of this very well-known framework by Turi and Plotkin, which applies to first-order systems. So let me quickly walk you through how this works in a nutshell. So again, example of the call by name untyped lambda calculus. So we have our syntax and our operational semantics. So the two blue rules are the standard ones. And for the purpose of this setting, I would also like to add this green rule that is usually left implicit, that essentially says if I have a lambda abstraction, then I consider this as having a label transition where the label is the lambda term, and I go to the term p with q substituted for x. Yeah? So the advantage of this is that I can regard the lambda calculus as a kind of transition system that has lambda terms as states, and just for every term says either I beta reduce to another lambda term, which corresponds to the left coproduct component, or I behave like a function that maps lambda terms to lambda terms, yeah? Right? So these are the two cases. And so this is the kind of thing we have to abstract here from. And so how does this work? Well, luckily, in the case of syntax, Fiore, Plotkin, and Turi have done all this for us a long time ago. They observed that one can model syntax of languages with binders, alpha equivalents, and so on, very nicely as initial algebras for endofunctors on suitable presheaf categories. And so our bold step is we just take any endofunctor on any category as our model of syntax and regard its initial algebra as the object of program terms, right? So we regard the initial algebra of a functor as an abstract object of programs. Then how do we model this operational model abstractly? Well, observe that the right-hand side, this lambda plus lambda to the lambda, can be written like this, b of lambda lambda for this bifunctor y plus y to the x. And so the pretty obvious generalization is what we call a higher order coalgebra, which is just a morphism of this type, where the b is now an abstract bifunctor of mixed variant, so covariant in one and contravariant in the other component, like this y plus y to the x on the left-hand side. But the most interesting step, of course, is how do we model operational rules? And this can be done by a concept called higher order GSOS laws, which is a higher order extension of this Turi-Plotkin idea. So a higher order GSOS law is a dinatural transformation of this type here, where the idea is that this transformation encodes the rules of the language into functions. So what this roughly says is you give me an operator of my language, like the binary application operator of the lambda calculus. Then you tell me how each of the operands behaves. So for example, you tell me that p beta reduces to p prime. And then I tell you what the output, what the next step should be. So in this case, go from p of q to p prime of q. So the sigma star here is the free monad. And so we can reduce into complex terms, possibly. Yeah? So that's the idea. And so we have understood all these things, syntax, semantics, operational model, abstractly. And what is quite neat now is that at this level of generality, we can develop and have developed notions of applicative bisimulation and, in fact, step-indexed logical relations. And so let me roughly explain how this works. So the rough idea is that, what is a bisimulation or a logical relation? It's a relation between programs, right? So abstractly, it's just a sub-object between the product of this object of program terms. And these relations must somehow respect the behavior, which is expressed by this gamma, this operational model. And the way how they respect the behavior is expressed by a relation lifting. So a lifting that promotes a relation R to a relation R on programs to a relation on behaviors. And since this notion is parametric in the choice of lifting, this gives us lots of freedom in expressing different properties of preservation of behavior. And again, at this generality, we have an abstract congruence result, or soundness result if you want, that says under some natural conditions on the law that encodes our operational rules, we can deduce that applicative bisimilarity is a congruence and the logical relation is a congruence. And what these conditions express roughly is that the rules are suitably polymorphic and they interact well with the weak transitions of the operational model. And this can be said abstractly. Maybe the key point I should make here is that these conditions are easy to check. They usually boil down to quickly looking at the rules of the language. And they're much easier to check than proving the congruence result from scratch. Because the complicated things like House method are hidden in the proof, and the user of the theorem doesn't have to know about this. Yeah? So it's quite a modular approach. Right, so yeah, this is mathematically quite pleasant if you are into categorical abstractions at least. If you're not, then it's not. But I like it. But of course, the elephant in the room is how useful is this? So does it apply to realistic languages with like interesting effects, interesting type systems, interesting forms of evaluation? And in this talk, I would like to focus on this evaluation part and specifically talk about call-by-push value languages in this context of operational abstract methods. So what is call-by-push value? This is a functional paradigm introduced by Paul Levy quite a long time ago. It is famous for elegantly subsuming call-by-name and call-by-value evaluation. So the two standard forms of evaluation can be nicely embedded into this. It has good support for effects, and it also has had some practical impact, although it was conceived as a mainly theoretical concept, for example, in compiler optimization and program optimization. So very briefly, how does this language look like? The key point here is that we have an explicit distinction between value types and computation types. So everything is either of value or computation type, and there are constructors that explicitly translate terms of the different types. So for example, if you have a computation, T, you can basically stop the computation, thunk it into a value, and then, for example, hand this value to a function. And there's a reverse operation force that does the reverse. And then there is an operational rule that basically says that it's reversible, yeah? And so on. So that's a very rough idea. And what makes this setting interesting for us is that operational methods for this are largely undeveloped. So to the best of our knowledge, there's no work on applicative bisimulations in this context. And to the best of our knowledge, there's also only quite limited work on logical relations. But for example, step index relations for recursive types have not been developed in this context. So this seems to be the ideal opportunity to test our framework and see if we can get these methods for free or for cheap. And indeed we can. And so how do we do this? Well, we have to model this language in our setting. And the base category is a suitable category of presheafs following the Turi-Plotkin-Fiore idea. In this case, presheafs over types and typing contexts. The idea being that we can model the set of terms as a presheaf of this type that takes as an input a type and a context and yields the set of all terms of this type in this context. Yeah? And with a suitable choice of categories of types and contexts, we can do that. And again, following this Fiore approach, this can be shown to be the initial algebra for a suitable endofunctor on this complex presheaf category. So what about the behavior? So we need to find this mixed variance bifunctor. And very roughly what this functor does is it takes two objects, x and y, and maps it to a product where the left component encodes the substitution behavior of terms. So it kind of explains what happens if you substitute terms for variables in CBPV. And the second component encodes the actual behavior of terms. So the three kinds of things that can happen: either you beta reduce, or you behave like a function, or you can be stuck, for example, if it's a variable, something like that. So the definition here is not very precise, but this gives you the rough idea what this functor does. Yeah, and now that we have this, we can instantiate our abstract notions and, for example, get a definition that says an applicative bisimulation for CBPV is a type index relation with 11 properties. Yeah, I will not list the properties here. The key thing is we get this definition for free, so you don't need ingenuity to come up with these 11 properties. You just take the categorical definition, instantiate it, and spell out what it says in this setting. Yeah? So no ingenuity needed. And similarly for logical relations. And by applying the abstract congruence theorem, we get almost for free the congruence theorem that says applicative bisimilarity is a congruence and therefore sound for contextual equivalence. Right, and again, similarly for logical relations. Yep. So the take-home message here is that by applying our setting, the definitions come for free, and the congruence theorem comes for very cheap. Yeah? So it's not completely free because we have to check the conditions of the abstract result. But as I explained earlier, this is easy. So this is done in 5 minutes. Yeah? And I would expect that if you gave this theorem as a task to a PhD student who doesn't have these operational methods, the abstract methods as underpinning, this would easily take half a year or something to come up with all the definitions and deriving the theorem. And here it's quite easy once you get the modeling of the result. Right, so to conclude, I asked, does it apply to realistic languages? And I think now we can at least partially be very optimistic about this. So today I talked about CBPV, but we have also lots of ongoing work on interesting type systems like polymorphic types. And we are also actively working on languages with state and references and quantitative languages with probabilities where you could, for example, talk about notions of distances of programs and nice congruence properties of them. Right, that's it. Thank you.
Hi, Max New, University of Michigan. So one of the things I love about call by push value is it has very nice categorical models itself, right, in terms of adjunctions, right? But I didn't really see anything that was analogous to that structure here.
No, it's a completely different kind of category theory. I mean, even if you think of like simply type lambda calculi, you have these nice closed categories and so on, right? But for some reason, this does not appear at all in this theory of operational methods. So it's a completely different kind of categorical method that we do here.
Okay.
Yeah? So this is completely at the level of coalgebras and relation liftings.
Because I was wondering if you could approach maybe having an abstract setting, for example, parameterizing by the notion of effect, or you could get out, for example, an adequacy theorem relating the denotational semantics and your operational semantics.
Yeah, that's a very good question. So denotational semantics in general is completely out of reach right now because there is a very little categorical understanding of what does it mean to have denotational semantics, right? I mean, it's again something that you have for classes of languages, but you would, if restricted to classes of languages, I agree, there must be some connection. Yeah.
Thank you.
This seems very nice. Yeah, Sam Lindley, University of Edinburgh. So you've shown that you can synthesize a logical relation in a setting that hasn't been studied before. If you apply this into systems that have been studied before, do you arrive at exactly the same logical relation that you see in the literature? Or?
Yes. So, yes and no. So, in previous work, where we synthesized these abstract definitions, we really mainly applied it to standard, for example, type lambda calculi with recursive types. So very simple settings. And there we recovered the usual notion, or at least an equivalent one. When it comes to more complex settings, like
how about the
polymorphic types and so on.
What about the last talk?
Well, I wondered myself, but I can't answer that right now. It's not obvious. Yeah, it's not obvious. So, I mean, right now our steps are ordinals. So, I mean, I think as far as I'm aware, sometimes the steps are more clever. it's probably not always exactly equivalent. Yeah? But it might be a relation that still is usable for the same purpose, even if it's not equivalent. Yeah?
Hi, I'm Cheng from UCL. Thank you for the talk. So I was wondering, in the sigma functor, can you encode algebraic structure in there, like in the sense of equational theory? And if so, does your work have any implication on the connection between coalgebra and algebra, like coalgebraic completeness theorem and stuff?
So currently not. So basically what you're asking is, can we replace the free monad by any monad, basically, right? It's an interesting question, but right now for the operational theory, we really need the freeness of the monad, because we have to, essentially we need to define this operational model on program terms by induction, right? And so, well, we had to. Now there's ongoing work where we don't have to, where we can just postulate that we have it, and this, I think, might work in the context of equational theories, but there's no definite answer yet. No.
Neil Krishnaswamy, University of Cambridge. So I had a question about the expressiveness of your transition systems. So it looked like they were basically some variety of generalized labeled transition system.
Yes.
But many operational semantics have like a lot more stuff in the format, like a heap or like a continuation or something like this. Are these still expressible as?
They are to some extent expressible. Something that we are actively working on right now is stateful languages, so which was very much in the direction of your language, of your question. And it's quite tricky. But the idea is that you can sometimes encode the heap into your syntax, and by doing that, you can include the heap into the model, and so the heap would be implicit in this mu sigma. Yeah. So at least in the case of standard while languages with references, we are in the process of doing that. Yeah.
Okay, thank you.
Arthur from Yale University. So you said you get these definitions for free, but of course that's conditional on first defining a suitable presheaf category, right?
Yeah.
And then also being able to encode your operational rules as this profunctor-like things.
Yeah, this dinatural transformation here, this one. Yeah.
So how hard it is to make the conversion?
Yeah,
to come up with this
it's a very reasonable question. So I would say it's not hard for us because we have gained a lot of experience with this. But what is really needed, and that's a spot-on question, is kind of a dictionary of the kind of structures that you need to model different features of languages. Like, for example, if you have binders, you want what do you want in the exponent of your presheaf category? If you have types, what do you want in your presheaf category, right? And kind of a meta theory of this. So what kind of categorical structure reflects what kind of language feature is still missing. So we are gaining experience, but this is definitely something we want to do. There was another question. Oh. Yeah.
Hi, thank you. I'm Anthony from University of Illinois. So with this categorical framework, sometimes I wonder, whenever you have a programming language and you add in a new feature, maybe you start off with simply type lambda calculus and now you add recursive types. Is there, using this framework, a way to start with the categorical abstraction for the smaller language and then extend it and then recycle some of the congruence proofs that you already have? What does that kind of look like?
Right. I mean, so I would say it's not directly the case, but because, I mean, yes, so for example, if you go from simple types to recursive types, it just means you change your category of types, basically, right? And all you need to do is check whether the conditions of the congruence results still hold. And since the conditions are very natural, usually that's a matter of minutes. Yeah? So it's very little work to extend languages.
Is that true also for, say, store? Or
For store, it's not true. So for type systems, it's true. Well, it tends to be true. For effects like store, it's tricky. So it's what I just said. You have to kind of include the store into the syntax. We are currently working on this and writing a paper on this. But this is actually tricky. Yeah.
thank you.
Yeah.
Okay. All right. So let's take the remaining questions offline, and let's thank the speaker again.
Right. Thank you.